Okay, we are continuing on here. We were talking about electron configuration, which I think is chapter 11. So remember, electron configuration is sort of the order at which electrons go into the atom. They do go in, as we've talked about, lowest energy orbitals first, and they continue to sort of fill from lowest to highest until they all get filled. There are s orbitals. There are p orbitals, d orbitals, and f orbitals. And remember that basically the maximum number of electrons you can put in any individual orbital is going to be 2. And because there's only one type of s orbital, that is 2 electrons you can fill in. Remember, though, that the p, the d, and the f orbitals on each energy level are considered sometimes subshells because they come in groups of individual orbitals together. So the p orbitals, there are 3 different types. The d orbitals, there are 5, and the f orbitals, there are 7 different types of them. Again, taking all those sort of orbitals together, all the p's together, all the d's together, all the f's together, they're considered subshells or sublevels. That means if you filled up the p subshell, you could put 6 electrons, 10 in the d subshell, and 14 there in the f subshell. The order also can be determined by sort of recreating our little sort of key here, and it based off of what we talked about, that on the first energy level, that's where s's occur. The second is where p's occur. The third is where d's occur. And the fourth is where f's occur. And just by remembering that, kind of put it in a diagonal like that, you then can just fill in all the numbers underneath it, and you pretty much will have the order. Again, you just kind of keep the letter and just keep going down. And D's actually only go to 6. And F's really only go to 5. Remember that we always basically start here, we zigzag back around, and we continue our sort of pattern. And that really is where most people kind of mess up. As we see here, and as we talked about last time, the S's are actually lower in energy than the D's. So they do get the electrons first, and then they go into the D's. And that pattern continues after 4s and continues with the 5s going back to the 4d. And if you remember basically those 2 things on the board there, you pretty much can write any electron configuration that you would need to. We also talked about the idea of orbital diagram, which is basically either lines or boxes to represent orbitals. And remember that the first electron goes in the upwards direction, the second one goes in the downwards direction. And that's what is referred to as being paired spin of those electrons when they're going opposite directions. I think we finished last time talking about what happens when we do get to a subshell that has multiple individual orbitals available. And when we do get to that situation, this is, say, the 2p subshell, they actually do go in each orbital basically one at a time. And the idea behind that is what's referred to as Hund's rule. And it says that the most stable arrangement for electrons is parallel spin. So that keeps them all going in the same direction. At that point, we would kind of run out of room. So we then would go back after we give each one a single electron. We would go back and then start pairing them off. And then obviously until it is filled as well. So that happens with our P subshells, one at a time, come back and fill. Happens with our D subshells as well, one at a time, come back and fill. And also our F subshells. Each of those boxes represent the different, for example, p orbitals. This represents the first boxes like the px orbital, the py orbital, and the pz orbital that happens. Remember that they basically are in sort of 3-dimensional space, sort of different orientations in 3-dimensional space is basically what those are. Any questions on any of that stuff there we talked about last time, I think? Okay. So I think we left off with nitrogen. So once again, nitrogen's atomic number is 7, which means it has 7 protons, and would also again have 7 electrons in a neutral atom. So if we wrote the electron configuration here for nitrogen, we would start with 1s2. Again, we would zigzag back on our little chart. It would take us to 2s2. Zigzagging back there would then take us to 2p3. Remember that when we sort of write the configuration, it should look like that: 1s2, 2s2, 2p3. Once again, there's no commas, no dashes or anything like that when you write the electron configuration. You just lay it out like we just wrote it. In addition, remember that the first number there is the energy level. So basically what this 1 here represents is the n equals 1 level. So on the very first energy level, we basically have 2 electrons in the s orbital. This guy would be on the second energy level. So would that guy. So those guys would both be on the second energy level, a little further away from the nucleus. And we have 2 electrons in the s orbitals, and we have 3 electrons there in the p orbital, which means we have a grand total of 5 electrons on the second energy level and 2 electrons on the first energy level. Once again, if we did our sort of orbital diagram, we'd have our appropriate boxes. And again, we're not really drawing this properly in terms of energy, but just to save space, we'll go across, bless you. And again, here we would continue to fill our electrons one at a time in the upwards direction, which represents positive half of spin in terms of the electrons. At this point, we can see a couple things looking at the p subshell there. We basically will now have to start pairing people up as we come in with our next electron. And we also have room for 3 total more electrons before that p subshell is filled. Any questions on that one there? All right, so we might as well finish out the first 10 here. So we'll go to oxygen next, continuing on with the configuration. 1s2, 2s2, 2p4. Once again here, filling in our orbital diagram, up and down paired off, up and down paired. Again, going one at a time in the upwards direction. Now that 4th electron will come back to the first box there, our first orbital, and we will pair it off in that first orbital, which in this case would be the px orbital. Now we can see we have basically 2 spots left until we fill it up. So again, we'll continue down to fluorine, which is number 9 on the periodic table. And fluorine, which is 9, would end up with 1s2, 2s2, 2p5. So we're almost there to fill the subshell. And our orbital diagram will look pretty much like oxygen, except that we'll have an extra electron pairing up. So once again, up and down, up and down, up, 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 down, and down here. Once again, leaving our last sort of p orbital available. And obviously that will happen when we go one more over on the periodic table to neon, which is 10. And that will basically fill up our 2p subshell. So let's take a look at that one there. So at neon, we end up with a configuration of 1s2, 2s2, 2p6. And again, at that point, we have now filled in the last electron in that subshell. So up, 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 and then down, down, and down. At this point, if we do have more electrons that we need to fill, we would have to continue down through our zigzag sort of chart there. And that should take you to the 3s orbital. Next would be where we would go. Any question on electron configuration, orbital diagram here? All right. So why don't you do Argon's configuration there? And while you're at it, why don't you do, yeah. Yeah, you could, the limit would be obviously the element. So, yeah, but yeah, so you go on pretty much, the 100 and whatever it is up there, technically speaking. So you do not obviously have to fill up all the orbitals with the electrons. You obviously would just fill what you need for that particular element. But yeah, it could kind of keep going, stuff like that. Other questions? All right, so why don't you do argon? Why don't you also do why not? Let us do, for the fun of it, let's do nickel as well. So nickel is I'm getting old, but I think it says 28 there. All right. If you want on this one, you can just write the electron configuration. You don't have to do the orbital diagram. So let's do the electron configuration for nickel and argon here. Okay, let's take a look and see. So we'll start with argon. So again, starting at the top of our chart, we should end up with 1s2. Then we got to go to 2s2, then to 2p6. Once again, here, if we count up the top numbers, they'll tell you how many electrons you already distributed. So 2 and 2 is 4, and 6 is 10. So we got 8 more to go. After the 2p, we're going to go to the 3s2. And that would now be 12 total electrons. After the 3s will come the 3p6, which once again, if we count up the top numbers there, we should end up with 18 in this case. In this case, we have 8 electrons on the third energy level, right? 2 in the s and 6 in the p. We also have 8 electrons on the second energy level, and we got 2 electrons on the first energy level. Any question on that configuration there? All right, so let's look at nickel, which is 28. So we'll take a look at nickel here. It would be 1s2, 2s2, 2p6. Once again, here we'll go 3s2, 3p6. And at that point, that is 18 still. The next is, again, it is the 4s that comes first. So it will be 4s2. And then we zigzag back to our 3d subshell at that point. And we will end up with 3d8 in this case. We add up the top numbers there. Should equal 28, I hope. Yeah. Any question on that configuration? So again, that is a very common mistake people make. They gotta go to the 3d, then the 4s. Again, in terms of filling, the 4s orbitals are lower in energy than the d's, so they will get those electrons first. Any question on any of those two? Yeah. Yeah. There was. So if we want to, we could steer real quick here. So if we take a look at it, we would have, and again, I'm just going to go sideways here for space saving. So we have our 2s, we would have our 3 boxes for our 2p. We would have our box here, our line for our 3s. We would have our 3p there. We would have our 4s, and then we would have our 3d here, and it basically would feel like this: 1 up, 1 down, 1 up, 1 down, up, 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 come back and pair, up and pair. Again, to the p, we would go 1 at a time, and then come back and pair. This would go up, this would go down, and then with the d, same thing would happen. We would go up first, so that's 1, 2, 3, 4, 5, 6, 7, and 8. So it looks something like that. Yeah. Other questions on that? Now, when we also look at these two sort of configurations together, the top one being obviously argon here, and the bottom one there being nickel. When we look at this part of nickel's configuration through here, that configuration is how many electrons? Is 18, which is essentially who on the periodic table here? It is basically argon's configuration, right? So that first little part there is basically argon's configuration. So there is sort of a shorthand that is sometimes used with electron configuration. Some people sometimes refer to as noble gas sort of configuration. And basically what we do is, because a part of, say, nickel's configuration is basically argon, you could shorthand it and go in brackets argon, which would represent the electron configuration for argon. And you would just continue on with the rest of the electron configuration there. And you would have argon, 4s2, 3d8 in this case. What goes in the bracket is always a noble gas. So it's always group 8. It's always the noble gas of group 8 that comes right before the element you're writing your electron configuration for. So for example, if we looked at magnesium, which is 12, 1s2, 2s2, 2p6, 3s2, there would be magnesium. If we take this part of magnesium, that is how many electrons? That is 10 electrons on the periodic table. 10 is neon. So we would put neon in little brackets and continue on. So that's sort of a shorthand for electron configuration. It is always the noble gas that comes right before the element that you are writing. Yes. I did that for gold. Very good. Yes. Yeah, you could do it for any of the elements, including the transition metals. It doesn't matter. You just basically back up to the noble gas that comes right before it, and you just kind of continue on with the configuration. Any questions on that there? All right. All right. Now, the idea of the off-ball principle is sort of based on the idea that protons are basically added to the atom one at a time, and we sort of add electrons really kind of the same way. They're added one at a time to the atomic orbitals. Again, lowest energy first, following really the couple of other important rules that we talked about last time. Again, Pauli's exclusion rule, which is the one where, again, if you have two electrons in the same orbital, they have to have different spins. So one up, one down, they're paired. And again, our Hund's rule, which says, as we just talked about, maximum stability there going well direction. So here's another example. This is potassium. Again, if we take the first part of potassium, we once again will have argon's configuration, which is 18, and we can continue past it with the 4s1s. You could write it either way, unless it explicitly tells you not to use the noble gases. But other than that, you could write electron configuration either way. Any questions on that there? Now, transition metals, which again are between group 2 and group 3 on the periodic table, they have incompletely filled d orbitals. They also give rise to cations, which incompletely filled d orbitals. There's actually several exceptions to the electron configuration in the transition metal region. There's a lot of exceptions that if you follow sort of the zigzag sort of method there, you'll actually get maybe the incorrect electron configuration. But for our class, we're just going to worry about two notable exceptions, which most people sort of think about. And that happens in the first row, transition metals, and that is copper and chromium. Chromium being 24 and copper being 29. And for example, if you do chromium's configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4. This is what you would get if you followed our zigzag sort of method here. And chromium, along with copper, has been found to be experimentally more stable with actually an extra electron up in the d orbital and one less electron in the s orbital. So basically the exception is one of these electrons basically come up over into the d orbital. And it also happens there with copper as well. So chromium's configuration, if you shorthanded it, would be argon 4s1 3d5, and copper would have the exact same sort of exception, except that it would then fill up all of the d orbitals with electrons and have 3d10. It's able to do this really because the 4s orbitals, for example, and the 3d orbitals are really, really close in energy. So they're very, very close in energy, and it doesn't take a lot of energy for that electron to kind of pop up into the higher energy level. What actually happens when we start actually filling the d orbitals with electrons is they actually end up switching in energy. So what actually happens is the electrons go into the 4s first because it's lower in energy. And then as you actually start populating the d orbitals with electrons, these two guys actually end up switching in terms of energy. And you actually end up with the 4s electrons being higher in energy than the 3d electrons. And this is why sometimes you will see electron configuration written like an order. They'll write it like 3s2, 3p6, 3d4, and kind of put them all in order. And that is electron configuration written based on energy rather than filling. And just so we're clear, in this class and pretty much every chemistry class you take, you write electron configuration based on filling, how they go into the atom, which means the S's come first and then the D's. I've only took one class in my whole life where they wanted you to write it the other way. But in reality, what does happen is it does switch. Those energy of those orbitals do actually switch. Where that's going to be important is, as we'll talk about here, when they start losing electrons. So when transition metals start losing electrons, they actually lose different electrons because there's this switch in energy. But when the electrons go in, and how you should write the electron configuration, again, is the filling order, which is the S should get it first and then the D. Now for us, chromium and copper are the two exceptions that you need to know. Just so you know for real, if you go under chromium and copper on the periodic table to like silver and underneath, and then kind of in between those two, there's a lot of more of these type of exceptions where there's extra electrons going up into the D. For example, PD has no electrons in its S. They've all went up to the D. So, you know, there's a lot of exceptions. Silver is an exception as well that has a similar type of situation occur. So usually chromium, copper below, and then kind of in between them. There's a lot of these exceptions. But for us, again, you're just responsible for chromium and copper. For anything else, you could write it following the zigzag thing. Just know in reality is probably incorrect for some of those in that region. Any questions on that there? Okay. And again, they see chromium and copper exception at the end. So the Laughingide and Octonized series, which are our guys on the bottom, that is our place where we do start to get into our F subshells, 4F for the Laughingide, 5F for the Octonized series. And again, they give rise to completely or incompletely filled F subshells. Now, when we look at the periodic table, you could actually count off electron configuration using the periodic table. The first two groups, group 1 and group 2, that is what is referred to as the S block. That's because S has how many electrons? 2, 1 and 2, basically. Yeah. From group 3 to 8, that is what is referred to as the P block on the periodic table. And that's because P subshell can hold 6 electrons, which would be 1, 2, 3, 4, 5, and 6, basically. The transition metals is our D block on the periodic table. And that is because you could hold 10, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. The 2 rows, which are not on this picture here, that is our F block. The 2 rows at the bottom there, the Laughingide and Octonized series. If you count across there, there's 14 boxes, which is the 14 electrons. So for example, the period numbers that we see on the periodic table, that's like our n equals 1, n equals 2, n equals 3 sort of number. So for example, if we were doing magnesium, which we did previously, we would start up here, and right here at hydrogen would be 1s1 to helium, which would be 1s2. This is now period number 2. This would now be 2s2. This would be 2p6 to the end. We're now in the 3rd period here. This will now be 3s2. So you could actually count it off if you like. You could go down to, say, calcium, which would then continue. This would then be 3p6. And then this is now 4s2 is a calcium. So you could count off electron configuration from the periodic table, but you do have to kind of understand a couple important things. One important thing is d orbitals start on what energy level? D orbitals start on 3rd energy level. And this guy right here, even though he's on the 4th level here on the periodic table, is actually 3D. This guy would be 4D. This guy would be 5D, and this guy would be 6D. So that's the difference you got to watch out there. And also, the Ds are 1 behind the period number. Our Laughingide and Octonized series here should technically go up there at period 6, but this is F. So the Fs are actually 2 behind the period number. So it gets a little crazy down in that region. But if you pay attention and understand that, we could go down to our nickel we just did. So we had our 1s2, our 2s2, 2p6, 3s2, 3p6, 4s2. And literally at this point, you could go 3d, 1, 2, 3, 4, 5, 6, 7, and 8. And just count out the boxes, and you can get your electron configuration. Any questions on that there? I clearly was 1 slide short of that lecture, but here it is. There's our apps there. There we go. Just ahead of it, I guess. So here's our 4F and our 5F, which again does go here. So these guys are 2 behind the period number. The D is 1 behind the period number as well. I personally would recommend doing the zigzag guy that we made earlier, because there are little places here where you can, if you sort of count incorrectly, but you can use it in a quick way or to check yourself if you want, or if you feel comfortable doing it, you can do that as well. Now, let's talk a little bit about, go this way, I think. What happens when things do get charges? So let's say we had our magnesium that we did earlier, which was 12. Now, if magnesium made a +2 charge, how many electrons would it have? It would have 10 electrons in this case, right? +2 means it lost 2 electrons. So its configuration would be 1s2, 2s2, 2p6. And that is 10 electrons, which is who on the periodic table? Is neon's configuration. So magnesium, when it loses its 2 electrons, will end up at neon's configuration. If we took, say, nitrogen, which we did earlier, 1s2, 2s2, 2p3 would give us nitrogen. If nitrogen ends up with a -3 charge, it will then have 10 electrons as well, right? It goes 7 plus 3. It would then have a configuration of 1s2, 2s2, 2p6, or again, neon. So all three of those things in this example, magnesium with a +2, nitrogen with a -3, and neon all have the same electron configuration. That is what is referred to as being isoelectronic with each other. So something that has the same electron configuration but are different things are referred to as being isoelectronic with each other. That is the basis of bonding, pretty much. Ionic bonding, the metals lose electrons, and what they end up doing is backing up to the noble gas that came right before them. And nonmetals in an ionic compound will gain electrons and go forward to the noble gas that comes right after them. So if you look on the periodic table, after nitrogen is neon is the noble gas, so it ends up there. And if you look behind magnesium, it is also neon. And that is the basis of all bonding, as we'll talk about, is everybody wants to end up with the same electron configuration as the noble gases because they're incredibly stable. And just so we're clear, something is isoelectronic, it doesn't become that element. It has the same electron configuration as that element, same number of electrons, still has the same protons to keep it as magnesium and stuff like that. But it ends up being the same number of electrons, which makes it really stable. And that's the purpose of all bonding, as we'll talk about, ionic bonding, covalent bonding. The purpose of it is everybody to get to basically the noble gas electron configuration because it's really, really stable. Yes.
I made some predictions as to what for undiscovered on my paper.
That's good. We'll take a look at those later. Now, when we talk about transition metals, as we talked about a little bit earlier, they are a little bit different when they do lose electrons. So if we look at, say, iron, for example, which is 26, I believe. If we write the electron configuration for iron, which is 26, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 1, 2, 3, 4, 5, 6, 3d6. Now, when iron makes a +2 charge, it will actually end up with 24 electrons as it lost 2 electrons. Now, this is where we were talking about a minute ago about the orbitals of the 4s and the 3d, that the 4s is lower in energy, but then there's sort of that switch in energy that occurs when we start filling in the d electrons. So in the case of the 4s here, or 3d, this is again how it feels, but once we start doing that, we do get that switch in energy that occurs. And what ends up happening, as I mentioned, is the 4s actually ends up being higher in energy. And the 3d ends up being lower in energy. So what happens when things lose electrons is they typically will lose the highest energy electrons first. And that is because technically they are further away from the nucleus and not held as tightly. So those are the ones that go. So with transition metals, what will happen is because there's this sort of switch in terms of the energy of those orbitals, they will always lose the s electrons first. So in this particular case, when iron would go to lose electrons, it would actually lose these 4s electrons first, and it would lose both of them in this case. And that would leave us a configuration of 1s2, 2s2, 2p6, 3s2, 3p6, and 3d6 are argon 3d6. Now, if iron actually went to a +3 charge, it would end up with 20, bad math there, 23 electrons. So what happens in this particular case is the same thing is going to happen. We're going to lose those s electrons first. still need to lose actually one more. So what will happen is we will actually take out these electrons here, and then we got to dip into the D's next and take out the third electron. So we then would have to take out an electron from the D, and we would end up with a configuration of 1s2, 2s2, 2p6, 3s2, 3p6, and 3d5 are argon 3d5. So transition metals are a little bit different than representative sort of metals. Representative metals will, group 2 and group 3, they'll pretty much lose the last electrons in the configuration. Transition metals will always lose the s electrons first, and then if they need more, they will go into the d orbitals and start plucking out some d electrons. Any questions on that? Yeah. Yeah, so again, we write the electron configuration in the filling order, which would be what we have up there on top for the iron, that the 4s should get the electrons first, and then the 3d get them. And that's because, again, the 4s is lower in energy than the 3d. But what happens once that d starts to get populated is they actually start switching around. So you can kind of think of it at the end, once they're all kind of filled, there's like that shift that happens with the energy of those orbitals being higher in energy. So at that point, when it goes to lose an electron, it's actually going to lose those 4s because they actually end up being higher in energy once we start filling up those d orbitals. They go in first, but then they are lost first as well. So a good way to remember it, I guess. And it's only with the transition metals. So all transition metals, I think we had that picture a second ago. Actually, here, let's go this way. What's here, I think. There's that thing. Right here. So all transition metals, which are pretty much here, right? So these are all the transition metals here. When they do go lose electrons, these guys here will lose these guys first. These guys here will lose these guys first, and so forth, all the way down. So they'll always lose those s electrons first, and then dig into the d if necessary. So why don't we try one like we did when we do nickel with a +4 charge? What would be the electron configuration? Nickel, again, with no charge was 28, I think we did earlier. Okay, let's take a look. So once again, we'll look back at nickel with, again, no charge was our argon 4s2 3d8. Nickel now with a +4 charge means that it basically has lost 4 electrons from this guy. And it should end up with 24 electrons when it's all said and done. So once again, nickel, which is a transition metal, and even though, again, our electron configuration has the s coming first, it is at this point higher in energy. So we will lose the 2 electrons out of here, which leaves us still 2 more to lose. And those extra 2 will then come out of the D, and it would give us a configuration of, we kind of used a shorthand here, argon 3d6. Any questions on that there? Which again would be 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d9, 3d6 at that point. Any questions on things with charges and electron configuration? All right, so talking a little bit about valence electrons. Valence electrons are really the highest energy level electrons. They are actually the important electrons in terms of bonding because they're further away from the nucleus. They're held this tightly, and that allows them to either be lost or shared easily. And they are the ones in the highest energy level. So again, if we look at the configuration here of nitrogen, which is 1s2, 2s2, 2p3. On our second energy level here, we basically have 2 and 3, which would be 5 valence electrons here for nitrogen. The other electrons that are there are sometimes referred to as core electrons. So these would be our valence electrons. And these guys here would be our core electrons, which are obviously closer to the nucleus and held really tightly because they're sitting next to that positive charge. So it's going to hold them really tight. And they're not involved in bonding. So the valence electrons are always involved in bonding. Core electrons are not involved in bonding. And it's also the reason, as we'll talk about, why certain things make certain charges. And that's why they typically will only lose their valence electrons when they do make charges. Now, you could write the electron configuration for everything, but nobody really wants to do that if you are looking for how many valence electrons there are. So the number of valence electrons for anybody actually equals the group number. So everybody in group 1 has 1 valence electron. Everybody in group 2 has 2 valence electrons. Group 3, which is boron, 3, 4, 5, 6, 7, 8. So if we look at nitrogen, nitrogen is group 5. So that is how come it has 5 valence electrons, is those that we just highlighted. If we look at carbon, it would actually have 4 valence electrons. Oxygen would have 6. And our noble gases there would have 8 valence electrons, except for helium. Yeah. Helium actually has how many total electrons? 2. So it can't have 8 valence electrons if it only has 2, right? So outside of that, everybody else there in group 8 has 8 valence electrons. Helium has obviously 2. And again, you could go with the group number as basically equal to the number of valence electrons, a much, much quicker way to figure out number of valence electrons, which is important for bonding. So let's talk a little bit about some periodic trends as we go through this. We talked a little bit about when we did the lab, I think the other day, metals and non-metals. As you go down a group, especially in group 1, they tend to give up their electrons a lot easier. So in order of losing electrons most easily, cesium versus rubidium, calcium, potassium, sodium, and lithium. This is again because they are further away from the nucleus. They're not held as tightly. And I believe that is what we saw in that video we were looking at, right? Lithium reacted, then sodium reacted more, then potassium reacted a lot more. So what we saw, right, is as you went down the group, there's a lot more reactivity occurring. That's because as you go down a group, they're easily giving away their electrons, which is going to initiate a reaction occurring. Most active nonmetals are found on the upper right of the periodic table. And that is also what we saw in the experiment, right? Going up the halogens, except for our Dudek test tube, we saw that iodine was less reactive than bromine. Bromine was more reactive than iodine, and chlorine was more reactive than bromine. And obviously fluorine would be more reactive as well. So as we talked about, going up for our nonmetals, more reactivity, going down on the other way there for our metals, more reactivity for our metals. And that is because as we go up for our nonmetals, we'll talk about it, but they have a lot of properties where they pretty much want to gain electrons, take people's electrons, which is going to sort of initiate a reaction to occur as well. So speaking of one sort of trend on the periodic table, which is really important, that is what is referred to as ionization energy. And ionization energy is the energy that's required to remove an electron from the gas phase of an atom. It is essentially how we make a cation, right? When we lose an electron, it becomes positively charged. Metals have relatively low ionization energy, and nonmetals have very high ionization energy. Electrons actually do come off one at a time. So even though we think of something that's losing 2 electrons, they don't actually come off both electrons at once. So if we did something like magnesium, for example, that we've been talking about, the first thing that would happen again is magnesium would dump 1 electron, and we would write that like this, where the electron's on the product side of the arrow. What next would happen is magnesium with a +1 charge would then lose 1 more electron, become a +2. And, you know, perhaps it would then maybe lose another one, and so forth. So the electrons do come off basically one at a time, and there's an ionization energy associated with each of the electrons that come off. This would be the first ionization energy. This would be referred to as the second ionization energy. And this would be, for example, like the third ionization energy. If you had to guess, is it harder to remove the first electron or the second electron? It is harder to remove the second electron. What happens with the size of the atom when you lose an electron? Does it get larger? Does it get smaller? Does it stay the same? When you lose an electron, you lost some of your electron cloud, so everybody kind of moves in, right? And when all these electrons then move in, they are now finding themselves closer to the nucleus, right? Which means they're going to be held tighter, and it's going to be harder to remove another electron. And when you do remove another electron, they're going to come in even more, right? Making it harder to remove the next electron. So what we see here is the first ionization energy, not too bad. The second ionization energy increases as you take off the second electron, and the third ionization energy increases even more as you try to rip off the third electron as well. So the general trend between, say, first ionization energy, second, and third is it increases as you go, keep on plucking off electrons. So what about magnesium here? If we look at its configuration of 1s2, 2s2, 2p6, 3s2, why does magnesium, for example, only make a +2 charge? So what happens is after we rip off the first electron, right? By the way, magnesium here would have how many valence electrons? It would be 2. It's group 2, and it would be these guys right here, right? So these are core electrons at this point here. These are valence electrons. So as we rip off the first one, not too bad. That's a valence electron, not really held too tightly. Gets a little bit harder to take off the second one. But now when we come to, say, the third one here, what electrons are we into? We are into electrons, which started out pretty close to the nucleus and held very tightly, and now is finding themselves, after 2 electrons have lost, even closer to the nucleus and going to be held even tighter. And in the case of magnesium, it doesn't happen. It's like a almost like a 10-fold increase in energy if you wanted to do it, between the second electron and the third electron, and it just doesn't normally happen and stuff like that. So that's why certain things will only form sort of fixed charges or certain charges. So things in group 2, after you get rid of the second electron, you're kind of into the core electron. So that's why they kind of stop at a +2 charge and only form a +2 charge. And things in group 1, for example, after you remove the first electron, you have a giant jump in terms. It's like, again, 10 to 12 times as much energy to try to remove that second electron. Something like sodium will always be +1 in that particular case. So that's the general trend of first ionization energy, second ionization energy, and third, and so forth. But in general, first ionization energy increases as you go up and to the right on the periodic table. So as you go this way, it increases, and it decreases as you go this way. If I have a very high ionization energy, does that mean it is harder to remove an electron? If I have a higher ionization energy, it is harder to remove an electron because that's the energy needed to remove an electron. So if you have a really big number, it's very hard to remove an electron. It probably won't happen. If you have a very low ionization energy, that means doesn't take a lot of those electrons basically to be removed. You don't need a lot of energy to do so. Any questions on that there? Now, this also relates to a couple other things, which is atomic size. The size of an atom actually gets smaller as you go up and to the right, and it gets larger as you go left and down. And that is because as you go up and to the right, there's something known as effective nuclear charge. which is basically the positive charge that the electrons feel from the nucleus. It gets larger as you go up and to the right of the periodic table. So everybody's brought in a lot closer to each other. So you have a lot more protons happening on this side, makes it a bigger positive charge going to pull those electrons in, which means the overall size of the atom gets smaller. A little less happening here in terms of effective nuclear charge as well. So they don't pull those electrons in as far. So the overall size is a little bit larger as you go to the left. So a couple of other important trends that we should talk about here is electron affinity. So electron affinity is the energy change that occurs when an element gains an electron. And on the periodic table, it basically increases as you go to the right in general and decreases as you go down. It's not a perfect trend, but that is sort of the general trend that happens. If you have an affinity for something, it means you like it, right? So electron affinity basically would be somebody that likes to gain electrons. And as you go up to the right, that is what occurs. And you go down to the left, it has a low electron affinity. That is basically what happens when we make an anion. Somebody becomes negatively charged, right? Another important sort of trend is what is known as electronegativity, which is different than electron affinity. Electronegativity is the ability of an atom to bring electrons towards itself. It also increases as you go up and to the right on the periodic table, with our good friend fluorine being the most electronegative element you could have. And it decreases as you go down. We also talked about the size of a cation, which is positively charged, gets smaller, right? Because it loses electrons. What happens when somebody gains electrons? The size of the ion now becomes larger, right? It gains some electrons, so the electron cloud gets larger than its neutral counterpart. So these are some important trends on the periodic table, and let's kind of maybe put them all together here to talk about them. So if we draw a big periodic table, also known as a big box, I suppose. As we go basically up and to the right, the size gets smaller and gets larger or increases as we go down. As we go up and to the right, the ionization energy, which is the energy to remove an electron, increases. And as we come down, it decreases. As we go up and to the right, electronegativity, which is the ability to bring an electron towards an atom, increases and decreases as you go down. And electron affinity, which is basically the energy change when somebody gains an electron, increases as you go up and to the right on the periodic table and decreases as you go down. So when we take all these sort of periodic trends together, as we go up and to the right of the periodic table, we have things that are really small in terms of overall size, which means the outer electrons are really close to the nucleus and going to be held tighter. And then we see that because it takes a lot more ionization energy to remove an electron. And they have a high electron affinity, which means they like electrons. And they have high electronegativity, which means they like their own electrons, but they also want your electrons as well. And all those things is what